the history of logarithms.
Nowadays, the logarithms are used to solve different kind of problems, like calculation of interest rates in the banks, finding earthquakes magnitudes, or finding the concentration of pH on acids in chemistry. But all of these are modern problems to use the logarithms for. And the logarithms were invented around 4 centuries ago, and every single time humanity makes a new discovery is because they were trying to find a tool to solve another problem. What kind of problems needed of logarithms around 400 years ago? Think about it. So this is when, who, why, and how invented logarithms.
We're talking about the 17th century, where the mathematical development was potentially huge. Scientists like Newton, Leibniz, Pascal, and Fermat were about to discover fundamental concepts for the science history. But before every great discovery, great tools must be used, and the way of making multiplications to make such calculations must be renewed. It is interesting how two scientists can be working on the same idea at different places. So, at the beginning of the 17th century, John Napier and Jules Burgi published their work about logarithms.
Calculations nowadays are really easy to do. We have calculators. But place yourself around the 17th century. And the science development was racing. Scientists were about to make huge discoveries and theories on science. But those huge theories needed every time more complicated and specific calculations. And the task of multiplicating really big or really small numbers was slowing down the development of science. Imagine yourself trying to multiply all those numbers a lot of times every day. Multiplication with a lot of numbers and really small numbers is not as simple as an addition with a lot of numbers too. It may take a little bit of time, but it's not so complicated. So it was then when John Napier thought that there must be one way to make multiplication as easy as addition, and that's why he started his investigation about logarithms. John Napier started thinking that it is actually really easy to multiply really big numbers that are a factor of 10. It is just about counting how many zeros has one factor and how many zeros has the other factor, and then you just sum those zeros and there's the result. So why is it so easy to multiply factors of 10? I mean, he thought 10 is a number, just like any other number. So exactly the same process must be possible for all the other numbers, isn't it? So he developed these kind of tables.
To know the result of 8 times 4, you just have to find the logarithms. So, the logarithm of 8 in base 2 is 3, and the logarithm of 4 in base 2 is 2. Then, summing the logarithms, you find that the power is 5. So, the fifth power of 2 is 32. So, the answer of 8 times 4 is 32.
But it was not really useful if you could only multiply numbers with the same base. So he made a table with the powers of a really close to one number. This way, almost every decimal number was included in the table, and if it isn't, you could make really close approximations that would give really certain results.
Here's a logarithm table in base of a number that is really close to 1. As you can see, the rate of change of the table is really small, meaning that for almost every number you may have to operate, there will be a really close approximation, or even the same number. For example, let's find 5.2164 times 20,744. We have to find the logarithms. So the table says that the logarithm of 5.2164 is 1,654. And the logarithm of 20,744 in the table is 9945. So now we have to sum the logarithms. Here we have that 1654 plus 9945 is equal to 11,599, meaning that 5.2164 times 20,744 is equal to 108,358. And this is how the logarithms made multiplication easier in the 17th century, giving the science the possibility of developing itself way faster than it used to.
So now let's see what they exactly mean.
The inverse of a function is graphically represented as a reflection. Now let's check this function, an exponential one. The graph looks like this. Now let's find the inverse. And let's graph it. As you can see, when they are together, have a reflection. So the inverse of a function is a reflection represented graphically. Now let's find the inverse of this function algebraically. Let's solve for y. It's quite complicated, isn't it? So this is why logarithms are for. A logarithm is a representation of the inverse of an exponential function. The logarithms are used in open files. They can be used as they were used in the 17th century to make difficult calculations just by summing exponents found by logarithm. They are also used in graphical tasks as animation, or also representation of economic tables that have inverse behaviors of an exponential function. But algebraically, they are mostly used to solve for variables on the exponents, like in this case. To solve for x, first we need to analyze the parts of the equation. We have the result, that is 4096, we have the base, that is 4, and we have the exponent, that is x. To solve for x, we need to use a logarithm, so we rewrite the same equation in the form logarithm in base 4 is equal to x. Now, we must find how many times do we have to multiply 4 by itself to get 4096. 4 times 4 is 16, times 4 is 64, times 4 is 256, times 4 is 1024, times 4 is 4096. Then we just have to count the 4s, 1, 2, 3, 4, 5. And now we have that logarithm in base 4 of 4096 is equal to 6. This is the principal algebraic use for logarithms, and this way the exponential equations are easier to solve.